Describing functions. How can you tell if a function is linear? Well, let's kind of review a few things before we get started. Some important vocabulary. Proportional and non-proportional. We need to remember that when a linear function is proportional, it goes through the origin. That means that the y-intercept is 0. When a linear equation or function is non-proportional, it does not go through 0. It has a y-intercept of any other number but 0. When we talk about the difference between linear and nonlinear, we have to remember what the word line means, because that's hiding there in linear. We have a line that goes up and down here. Nonlinear could be an example here of this shape. This shape is called a parabola. This is the shape that we are going to concentrate on here in 8th grade. There are many other nonlinear shapes, but we're going to concentrate on parabolas. Now, the other last thing we're going to talk about is slope. Constant slope versus variable slope. And I'm going to use this line to talk for a second. We've worked on slope before, and we've said that we can do rise over run. So we'd have 2 divided by 2, which equals 1. We also know when we're looking for slope on a line, we can choose any 2 points on that line to figure out rise over run. And it doesn't matter what it works out to be because we're always going to get the same answer. That's what is meant by a constant slope. So a constant slope occurs in a line. Now let's talk about a parabola. Now, a parabola would be kind of hard for us to draw some triangles, but I'm going to attempt here a little bit to go from point to point just to get that rise and run idea. So this here is 2 over 2, which at this point 2 over 2 is 1. Let's pick another 2 points. Let's start from this point here, and we'll go to that one there. So from here to here, we have a rise of 3 and a run of 1. So 3 over 1 is 3. So already we can see we are not getting the same slope. I'm going to try it one more time. I'm going to go here, and to look for the next possible point, it could be way the heck up there. And if I was to draw that, that could be 15 over 1. So we could see that it's constantly changing. This is what we call variable slope. And in nonlinear parabolas, which a parabola is nonlinear, we're going to see variable slopes, slopes that are not constant. So we want to kind of keep that in mind. Now, I've made the statement to you guys about how all equations are not functions, or I should say all functions are equations. So what I want to do is kind of explain that a little bit in terms of something that makes sense to you about chocolate. All chocolate candies are candy. Not all candy is chocolate candy, which is true. There's Jolly Ranchers, Nerds, all kinds of things. They're all candy, but they're not chocolate. So the same thing applies with functions and equations. All functions are equations. Not all equations are functions. So we want to show you kind of a little bit how this works so that makes a little more sense to you. This would be the realm of equations, this big blue box. And in here would be the functions. If you think about it, this is all the candy and this is just the chocolate. We can see that functions are a part of equations, but that doesn't necessarily mean that all functions, that all equations are functions. Let's get some more into this a little bit. Here I have y equals 2x and y equals negative 3x plus 5 in our function realm. These are equations, and they're equations as denoted by an equal sign, because that is basically the definition of an equation, is that there's an equal sign. Over here, I have x equals 3 in the equation area. Now, x equals 3 is not a function because it would not pass the vertical line test. It's a vertical line through the number 3. So because this is not, this would be one input with many millions of outputs. So again, does not pass our idea of what a function is. So we need to keep in mind about what a function is or not a function while we're working on this. So let's start looking at a little bit of graphing here, and we're just as a review. So example 1's really a review for us where we've been and what we know. So we're going to try and take this x as our input and our y as our output and plug it into this equation here, y equals x minus 2. So when we put a negative 1 into y, y equals negative 1 minus 2. Well, negative 1 minus 2 is negative 3. We're going to try it again with 0, so y equals 0 minus 2. 0 minus 2 is negative 2. We'll try it again here with 1. Y equals 1 minus 2. 1 minus 2 is negative 1. And the last one here, y equals 2 minus 2, which happens to be 0. Now all of these are ordered pairs, -1, -3, 0, -2, 1, -1, and 2, 0. All of these are ordered pairs. Let's put those ordered pairs on our graph. So -1, -3, 0, -2, 1, -1, and 2, 0. And then we're going to draw a line through our graph, just like so. Okay, and again, this is all review. We've been doing this for a while. Now we can take a look at this equation another way to graph it. And we've talked about this before. We can take the slope and the y-intercept of any equation and graph it. For example, y equals x minus 2. The slope of that line is 1 and the y-intercept is -2. We know that slope is a number and is represented by rise over run. So if I take the y-intercept of -2, and that's where I begin or start, and I rise 1 and run 1, I will end up right back on the line where I was. So we can see there are a couple ways that we can graph these. Now let's apply this to something that's not linear. Okay, let's try it at y equals x squared minus 2. Now you hopefully have noticed the only difference between the previous equation and this one is that now we're looking at an x squared. So let's do the same thing with our input and our output, and we're going to put it together and get our numbers so that we can plot this together. So y equals -1, and I'm going to square it, minus 2. So -1 squared is 1, and 1 minus 2 is -1. So far, so good. Let's go to the next one. Y equals 0 squared minus 2, which is 0 take away 2, which is -2. Y equals 1 squared minus 2. 1 times 1 is 1, and 1 minus 2 is -1. Now getting the same answer might worry us a little bit, but when we take a look at our x values or our inputs, we notice that they're all different. We know you can have the same output as something else, but not more than one output for every input. So we're still looking at a function, so that's good. Let's put a 2 in there. Y equals 2 squared minus 2, and that would give us 4 minus 2, which equals 2. And we'll do it one more time with -2. We'll take -2 and square it, and then subtract 2. So -2 squared is 4, and 4 minus 2 is 2. Okay, so let's plot these points. So we've got -1, -1, 0, -2, 1, -1, 2, 2, and -2, +2. Now that's not going to be a line, is it? Okay, this is our parabola that we were talking about earlier, right? So let's draw a parabola. Hopefully you guys draw a little better than I do. Let me flip this around this way. Make it look a little better. There I go. Okay, a little bit better. So there's our parabola, and that's hopefully what you all got. Now we're going to try and just walk ourselves through here a little bit and compare some things. So I'm going to put this side by side so we can talk about these two equations we just graphed, y equals x minus 2 and y equals x squared minus 2, and see if we can pull it together and what we can say about the differences, and also keeping in this format of y equals mx plus b, which we've been talking about for so long, and why this format is still relevant. So you notice I have a line over here because I want to show that both of these are passing the vertical line test. So both of these are functions. So that's really important to know. So we're talking about functions at this point, linear functions and nonlinear functions. Now, when we notice the x, the main difference is we have x to the first power and x squared. What that's telling us is when we had x to the first power, we made a line. When we had x to the second power, we made a parabola. And this is true for any time we have an x squared, we will get a parabola. Anytime we have x to the first, we're going to get a line. So it's really important to see that first distinction. Second thing to notice, we have this part here. This represents the y-intercept. We know the y-intercept is where the graph crosses the y-axis. So if we go up here to where our line was, we'd say that our y-intercept was -2. And there it is. The same is true for y equals x squared minus 2. We have that right there at -2. So that y-intercept also plays a part. Now, the last thing we're going to talk about is slope. Now, we talked earlier about how slope is constant and variable. So how could it be the same? Well, they're similar. Where the y-intercept is exactly the same, the slope has a little bit more of a similarity going on. So we're going to talk about that next. So let's take a look here at this equation, y equals 2x plus 2, and let's graph it. So we have that slope is 2, and that the y-intercept is 2, and I'm going to make that slope be 2 over 1. So I'm going to plot this. I'm going to put it at 2. Oops, sorry. Put it at positive 2, and have a slope of rise of 2 and run of 1. And I'm going to draw a line through that. And I'm going to make it black. Okay. So this one right here, this equation that we've just worked with, y equals 2x plus 2, we have what we call like kind of standard rise and run. Now, what's going to happen if the slope becomes a large number? And what I mean by that is, let's say if we make it larger, like y equals 5x plus 2, where that slope, we're going to change it to be 5 over 1. So in other words, it's going to be climbing faster. So again, we're going to start at 2, and this time we're going to climb 5. 1, 2, 3, 4, 5, and over 1. And I'm going to do this line in red so you can see the difference. Now, we're going through the same y-intercept. I didn't want to change anything else other than that. But you can see that when we're doing this, the line all of a sudden, it was black before with the 2, all of a sudden it becomes 5. This number is getting larger. As it's getting larger, the line is getting steeper. And that's an important concept. So as it gets larger, it gets steeper. That line gets a little bit steeper of an angle. Now, what happens when the slope is a small number? Well, let's try that. Let's try y equals 1/4 x plus 2. So again, we've got a slope here, and here's our slope, 1 over 4. And we're going to start at 2. We're going to go up 1 and over 4, 1, 2, 3, 4. And we're going to draw a line through that. Let's get a green line so that it all kind of coordinates a little bit. Okay. Make it a little bit darker green. There we go. Okay. So now what can we say about this green line? Well, the green line is getting flatter, isn't it? So let's kind of add a little bit more besides steeper and flatter. We can say, we know that a horizontal line, first of all, a line that just goes straight across, this has a slope of 0. And because that has a slope of 0, the smaller the number is, the closer it gets to 0. The higher the number, the further away from 0 it goes. The line tilts further and further and further away from 0, and will get steeper and steeper. So this is a concept we need to remember. We've talked about this before. Now let's apply this discussion to y equals x squared plus 2. Now, if we did that and we plotted some points, our standard parabola of x squared, and we start at 2, we know that the y-intercept is at 2, and we have some points we can plug in, and we would end up with this parabola. Now, let's talk about this. What if it was steeper? Well, what if it was y equals 5x squared plus 2? Well, that means that, let's say I put a value of 1 in here. Up here in this red one that we had, when I put in 1 into it, the answer would be 3. But now in this blue one, if I put 1 into it, this would be 5 plus 2, which would be 7. So it would just go at 1 and just shoot straight up to 7. So it's going to be very skinny, very narrow. So hopefully that makes a little bit of sense there. So if it's going to be very narrow when the number is large, what's going to happen when we do 1/4? Well, we know it gets closer to 0. So as a parabola gets closer to 0, it gets wider and wider and wider. And that shows that it gets a little bit flatter, to the point again where it's going to equal 0. Now, we've been talking about everything being positive. These are all positive slopes on the linear side, and they're all going uphill. We know if they were all negative, negative 1/4, negative 5, negative 2, they would all be going downhill. So how does that apply to a parabola? We know when it's positive, everything is like a happy face. It's going up. So when it's negative, we're looking at the opposite being flipping it upside down. So when we have a negative in front of an x squared, that means that our parabola is going to be upside down. So just some things to think about. Now, what about other values for the exponent? Just some ideas for you to think about. What about y equals x to the third power? We know if we put in values, what type of values we might get. These are numbers that when you plug in, you would get as your input, you would get as an output. Now what that does is it makes it kind of go in a curvy way. Comes swooping down and goes through here. This is what we call a cubic function. And again, this is remember we have here it's plus 0, so it's crossing right through that 0. It's proportional. But if we wanted to move the whole thing up to plus 2, it would be up there. If I wanted to say x cubed minus 2, it would go there. But right now we're at x cubed even, and so that's why that is sitting right there. And the same is true for this one, y equals x to the 1/2 power. We're really talking about y equals the square root of x. And again, we have valid points on there as well. We've seen 0, 0, 1, 1. The square root of 4 is 2, and there's other ones in between. What happens is it takes off from here and it goes off in this direction. We don't have it, it won't be below anywhere because you can't have a negative square root of a number. So that kind of gives you a little bit more about that. So let's try to put together everything we've learned today in one fell swoop. So let's see if we can kind of identify stuff. So the m itself represents the slope. We know that the b, this part here on the outside, represents the y-intercept. When x is to the first power or no exponent is shown, we know that this is going to show a graph of a line. When x is raised to the second power, and we've got an x squared here, that means we know that our graph is going to turn out to be a parabola. Hopefully this helps to be able to look at an equation and be able to describe it and what is happening.